which edge computing is extremely interesting. I find it absolutely, a brilliant idea, right? Computing on the edge and the mini computers and all of that stuff. But what I'm arguably going to talk about, so I'll give you guys a minute. If you want to leave, please feel free to do that, right? If you're here to listen about edge computing and suddenly you're stuck with causal inferencing, then it's like, I don't know. I'm going to see one movie and then suddenly, anyway. See, the thing is, I talk a bit about causal inferencing, and I've been talking about it a little bit over the past few years because I don't believe, but I know that this is changing AI completely. This is not a minor change in stuff that's going on, right? This is effectively saying that we're going to do things very, very differently from what has been or what is being done right now. Yeah. And so a lot of the new research that's ongoing today in computer science, in econometrics and statistics, some of it in quantitative psychology, and a little bit in physics, all relates to causality. And because the big challenge that we know is, what I like to say is that correlation is not causation. Everybody in our statistics classes from Stats 101 has been telling us that correlation is not causation. But if you ask your statistics professor, then sir, ma'am, what is causation? They'll just walk out of the room, right? They won't even answer you. Or they might throw something at you, but they won't have a good answer. And this is stuff that bothered me, and it seemed like not just bothered me, bothered probably many of you, and definitely bothered a man called Judea Pearl. Okay. Can we have the presentation? Whose work we will be talking about. Judea Pearl is, a legend in the field of computer science and artificial intelligence. He won the Turing Award 3 or 4 years back. So some of the stuff that we are going to talk about will be from Pearl, and the stuff that he is doing with his collaborators over the last 30 years to change the field. And I'll talk about it a little bit more. So this is a very commonly used graph here, right? On one axis, we have drowning deaths, right? Drowning deaths in a year, number of people who died from drowning. See the red light. But anyway, and here we have the log of ice cream production, right? Or ice cream sales. Yes. Now, what do you think? Do you think these two things are causally correlated? Ice cream production, drowning deaths. I mean, does consumption of a lot of ice cream cause you to drown and or vice versa, even worse, right? That people who drown and die consume more ice cream. I mean, that's just very counterintuitive to me. I don't see the logic. But please keep this in mind because and there are all sorts of there's a website called Spurious Correlations, and they just publish all these graphs, right? Divorce rate in the state of Maine versus per capita consumption of margarine, right? So I mean, people who consume margarine get divorced more. Who knows, right? I mean, maybe they do, but very tough to kind of establish causality there. But this graph, I'll come back to the one here, right? Ice cream and drowning deaths. But we know that there's a lot of these spurious correlations, right? And that is a problem, and that is a big problem because not because who uses correlations anymore. It'll be like, oh, I have linear regression. I don't even other than when like exploring data in Excel, I don't look at correlations. Fair enough. But as we know that what is linear regression? The beta. Right? All of you have seen this, right? So a linear regression is nothing but the divisor of the two standard deviations of y and x multiplied by the correlation of x and y. A linear regression is very, very deeply related to correlations. Right? Let's never forget that, right? We forget. This is, you've seen this stuff, right? So therefore, what we are saying is correlations, yes, but correlations can be spurious. Correlations do not often entail causation, right, or imply causation. And therefore, I'm saying that linear regression also then is not causation. All we are saying is that two things move together in the same direction, right? We see X and Y being related to each other, and then we make a stronger claim that logistic regression then is also not causation. Yes? Why? Because logistic regression is nothing but linear regression after a few drinks. Right? I mean, linear regression, you take the frequency table, you take the log odds of that, and you get it's a three-step mathematical transformation. It's basically a linear regression. You just have to solve it using a maximum likelihood. We all know that. It's trivially simple. So linear regression and logistic regression are not really different things. Nobody told me that earlier, but it's not, right? So we are stuck, and then we don't have causation at all, yes? And the founders of the field of statistics did not like causation. Irving Fisher, if you use the word causality in front of him, would really get upset and walk out of the room. He was that unhappy about this. So there are some other intelligent folks who started talking about causality. That does A really cause B? That is the question that I'm trying to answer, right? I mean, I don't care if A and B move together. That is an irrelevant question. In regression, in machine learning, the slide's gone again. I don't see my face. I've seen it enough in the mirror. But sorry. So what are we doing with machine learning? What are we doing with neural nets? Do we care about correlations? Do we care about two variables, X and Y, moving together? No, it's irrelevant, right? It's like those movies where people kind of mistake this car going behind them as if somebody's following me, right? They're not. They just happen to be going to the same destination as you. Nobody's following you. You're not that important. What I care about is that if that person is really following me or not, because if they are following me and they do look a little shady, then I'm gonna drive real fast and whatever. So there are a few folks who got interested in this, but none of them were, not really statisticians, so to say. Sewall Wright, great, fantastic work in social sciences, one of the earlier ones. But there are multiple postulates, right? Some of which we'll talk about. And then we'll see that how kind of that developed this whole thing. So when Koch was talking about the four postulates that should be met before a causal relationship can be accepted, he was talking about disease agents. And he said the agents must be shown to be present in every case of the disease by isolation in pure culture. So if it's in some of them, not in all of them, then the agent doesn't cause the disease. It might just also happen to be there. You know that this virus causes this disease only if it's there every time the disease is seen in a person. The agent must not be found in cases of other diseases. This is again questionable. The agent might be seen. Once isolated, the agent must be capable of reproducing the disease in experimental animals, right? Now, what are we doing? We are slowly moving to the domain of pure sciences. We are saying that, oh, you know what? If I can isolate this agent, which I believe causes the disease, and is seen every time this disease is visible, then if I can isolate it, I can give that same disease to a mouse, right, or a guinea pig. And the agent then must be recovered from the experimental disease produced, right? So I produce this or reproduce this disease in that guinea pig, then I draw some blood samples from that guinea pig, and the agent should be there as well. That is causality, right? So you see, it's a lot of very strong statements, right? You need to really think through a process. It's not linear regression, right? Before you can say that A causes B. Right? Even early on, people realized, this is like 150-year-old stuff, right? Hill again came up with his own criteria, and Sasser is again very important. He claimed that X and Y, there might be a causal relation if there are two things, right? Time order, which is X precedes Y, and direction, X leads to Y. This distinction, again, is very important to us. We'll come back to this. So the question then is, what about econometrics? We we know that in econometrics, we have these fairly advanced time series models, right? Arch and Garch models, many of you have seen that and stuff. There's something called grandeur causality, right? Grandeur, Nobel laureate, and so on. So, but what grandeur causality does very well, right, and which is why we study grandeur causality, is it looks at the intertemporal element of Sasser, that X precedes Y. Right? So when you run A/B tests, very common, right? A lot of us have run A/B tests. We make some changes, then we see that did something else happen based on those changes or not. So if the change, I color my website blue instead of black, which it was before, and I see a spike in people clicking on the shoes that I'm selling, I say, okay, you know what? The event X, where I'm coloring it black, is precedes, or coloring it blue, precedes more people clicking on it. Therefore, X led to Y, right? The time element. But then, and that's good. That's good. That's one part of it done. But the challenge there, and the challenge everywhere in the causal area, is about confounds, experimental confounds. I would like you to start thinking like an experimenter as opposed to a data scientist. Now, what is an experimental confound? Let's go all the way back here to our little picture here. Drowning deaths, ice cream production. Can you think of any relation between these two? They're numbers, fair enough. That's okay. Yeah, so the correlation is probably spurious. What else? Is there any reason that you can think of that drowning deaths and ice cream production or ice cream sales might be related to each other? Sorry? Number of people going outside, you're getting there, yes. Yes, very close. Shop is near a lake, but this is like the total numbers for a, but fair enough, I mean, by mom. Yes. Summertime. Fantastic. When do you go swimming? When can you drown in a pool? When you go swimming. When do you go swimming? You don't go swimming in winter. You'll freeze, right? Or it'll be very cold. You go swimming in summer. When do you consume ice cream? You consume ice creams in summer. So, yes, there is no causal relationship, right? But there is an underlying data generating process, right, which is common to both of them. No linear regression models, logistic regression models, any of your machine learning models, they don't look at this. None of them look at a separate underlying cause which might be causing both of these. You look at correlations or linear regressions or whatever have you, regression models, you say, oh, these two things move together. Sometimes you say X precedes Y, which is Sasser's first criteria, and you say, oh, you know what, therefore X leads to Y. But it might not be the case because there is something else which affects both of these variables. Right? And that can be generalized to the idea of a confound. The confounder, which is at the background, which we don't get to see, lands up affecting both the treatment and the outcome. We see the treatment and the outcome, and we say, okay, you know what, I gave you some medicines and you're fixed now. Maybe you know, the virus only runs its course for 4 days, and you would have been fixed anyways. You didn't need the medicine. Yes? And that is what we are going to talk about, because that to us is very important. Now, mathematically, probability of y given x, k is equal to small k, is greater than probability of y given k is equal to k, where k stands for some background variable. There's something going on in the background which you do not see, right? Okay. Now, there are, so anytime you talk about machine learning models, you still do not look at confounds. Probability of x given y at the end of a machine learning model, that's what we get. That's our outcome. That's all we get. If you think about, you know, whatever fancy model, or a random forest, great, very useful model, don't get me wrong. never implies causality. Right? It tells us the likelihood of seeing X if we also see Y. Right? Also, anytime you are getting to a probability of X given Y, it implies the existence of probability of Y given X in any machine learning model, which may not exist because there is an arrow of directionality. Sorry. Focus it there. No, this is not changing the slide. All right. Sorry, a glitch, but we're going to try and figure out a solution for this, right? Because we know that if you talk to a statistician, are any statisticians out here? No? Some, I'm sure, studied statistics at least. If you talk to a statistician and talk to them about neural networks, they would say, oh, you know what, it's our best curve fitting models on steroids. Right? There's nothing else, there's nothing new. You have better computing power, that's all you have. I don't completely agree with them, right? But not very far off. So you can say, we have AI, artificial neural networks, deep learning, CNN, RNN, and X can be anything NN, right? We just, newer and newer NNs coming out every day. I can't keep track sometimes, I'm getting old. But at the end of the day, what are we doing with neural nets? What we are doing with neural nets is exactly an extension of what we have been doing in statistics or in machine learning to a certain degree, which is we are looking at associations. This, according to Judea Pearl, right at the bottom, is seeing or association rules. Right? You can't read the slide, it's very pixelated, or I can't at least. And Pearl says, I can see this. It says that this is like animals. Your AI is as intelligent, or not really as intelligent, but similar in intelligence as my dog, or Pavlov's dogs, where he would ring the bell and the dogs would start salivating. Everybody knows about Pavlov's dogs, right? Every time you give the food to the dog, you ring the bell. Yes? So the next time, even when you don't have the food, you ring the bell, the dog starts salivating. And Dr. Pavlov thought that was very interesting to know. It is interesting, don't get me wrong. But associations, an animal can do. You don't need human level intelligence for associations, and that's where, unfortunately, AI is today. Right? I'll probably be thrown out for saying this. There are many people who will be willing to throw me out, right? But think about it. Think about the theory. Go back to the basics. Forget scikit-learn. Forget libraries. Forget about all of this stuff and look at any algorithm that you use today, any sort of neural network that you use today. All of it is associative. What neural nets do very well is it can extract features exceptionally well, better than anybody else before, right? Which is why it works on videos, it works on sound, it works on pictures. Great, feature extraction, fantastic. And then it runs a lot of iterations of the same thing. Why is it that neural nets are run on GPUs? They don't even need CPUs. Why? Because GPUs are very stupid. GPUs can do the same thing over and over again. They can't do any complex tasks. Let us go back to the basics. The reason why folks started using GPU, Andy New and his colleagues started using GPUs in Stanford back in the days, was because GPUs can do a lot of stupid tasks very fast, like they keep refreshing the screen over and over and over again. They cannot perform complex tasks like a central processing unit. We know that, right? So a neural net repeats the same thing, which is reweighting or recalibrating, right? It repeats that very, very fast, much faster than anything that we have done before. Fantastic. What's the problem with that? The problem with that is twofold, which to me is the biggest challenge that AI is facing today. One is, of course, at the end of the day, it's just associations. You're getting factors, you're getting features out, you're recalibrating weights really fast, still association, right? Second, you are going to be stuck at the limits of hardware. Today, any sensible neural net process that you run takes a very, very long time. People who work with serious neural networks, you ask them, how long does it take to run your neural net-based models? It takes a long time, right? It takes a lot of computing power. So you're stuck. You have a threshold. Yes. Now, Pearl says that the next level is intervention, right? These are kind of doing as opposed to just seeing. Today, AI can see, AI cannot do anything. What does that mean? That basically means that if there is an intervention of some sort, was the intervention effective or not, right? If I'm only looking at associations, how can I say that it was effective? How can you say with confidence that there was not a confound in your experiment which affected you before and after, and not the medicine? How can you talk about public policy, for that matter? Oh, you know what? I introduced something new. Yeah. Anything, goods and services tax. Now, maybe it was a great move, maybe it was a terrible move. I don't know. I'm not a politician nor a policy expert. But did it work or did it not work? Did it actually lead to improvements or not? Right? I have an aspirin, my headache goes away. Was it the aspirin? Or because I popped the aspirin and went to sleep? The underlying confound is I was probably just not getting enough rest. The aspirin did nothing. Yes? That intervention, again, are questions that yet cannot be answered by AI. And none of your ML models can answer this. Yes? Now, Pearl says that the third one is way above in the ladder of causality. And forget about AI doing anything like this right now. And that is counterfactuals. As human beings, we are continuously doing counterfactuals. What if I did not get through to the university that I actually went to? What if Hitler wasn't born? Counterfactuals, right? The human mind comes up with counterfactuals and goes in that direction very often and very fast. There are easier examples of counterfactuals. We're going to talk about counterfactuals a little bit more, right? Nothing so earth-shattering. But AI, or any model of AI or machine learning today cannot talk about counterfactuals at all. What if this did not happen, right? I see my y, which is my outcome. I have a bunch of x's. What if this x behaved differently? This x did not exist. What would happen then? What if I take out this x from the model? Not supposed to work like that. Doesn't work like that. Therefore, your AI does not and cannot potentially have imagination. Stable diffusion cannot give itself prompts. Any of you have seen DALL-E or Stable Diffusion, any of those text to visuals? Beautiful, fantastic, don't get me wrong, love that stuff, yes? But there is apparently a whole bunch of people who are selling Stable Diffusion prompts. Seriously. I mean, if you can sell NFTs, you can sell anything nowadays, right? Sorry, I'm sure there are a lot of blockchain guys who are going to kill me. But they're selling Stable Diffusion prompts. That is, if I give this particular prompt to Stable Diffusion, it's going to create a fantastic picture. But as of now, Stable Diffusion cannot prompt itself, right? Because it cannot really think like that. So we're going to go back to another old man, the Reverend Bayes, Thomas Bayes, right? Long time back. You have all seen this stuff, right? Conditional probability based theorem, etc. So what Pearl does, or predecessors of Pearl did, was they took the Bayes theorem, yes, which we have all seen in our statistics or data science or ML classes, and said that, what if there are multiple x's that affect your y? Okay? So all you're doing is you're taking the Bayes rule, you're adding a message passing algorithm to it. Yes? Because in the Bayes rule, the original Bayes rule, you have one A and one B. Probability of A given V, and then you can just flip it over and all this stuff. The easiest way to think about it is any Markov chain type model. Right? Markov chains, multiple things affecting each other going forward. Yes. So you have a Bayesian Markov chain. Okay, fantastic. So what that Bayesian Markov chain would do, right, when you have many x's, is that it will give you a time order, fair enough, which we already have seen, but it will also give you a directional order, because Bayes' theorem is very directional, if you remember. Right? Probability of A given B cannot be flipped over as is. Right? So there is a directional element to Bayes' theorem, where the Bayesian networks are saying that, you know what, I'm going to not just have the traditional Bayes theorem, I'm going to have a lot of these B's, right? And figure out that probability of A given B1, B2, B3, B4, and so on and so forth. Okay, great. The problem with doing that, there's only one problem left which you're going to solve, which Pearl solved, Pearl and his collaborators, which kind of brings us to the causal inferencing part. The challenge is that the moment you take this, right, Bayes rule, and try to have a lot of B's in there, you have to calculate a joint probability distribution for all of those B's. And that, when you have a couple of B's, it grows a little, right? But then it's going to exponentially blow up on your face. The more X's you have, the more and more of these joint probability distributions you'll have to estimate, and that really makes things, it makes things a little messy. Yes. So we move to what we get to is causal inferencing. Right? So we're going to talk about Pearl a little bit. We are after that going to talk about Guido Imbens, right, the recent Nobel laureate in economics, who talks about localized, average treatment effects in experiments. We're going to also talk about a little bit of psychology, and we're going to talk very little about physics. We're going to do that in the next 20 minutes. So, it's going to be rough. But a directional acyclical graph, right? What does that do? What it does is, simple example, I want to avoid slippery roads. Right? When calculating joint probabilities, we will use the chain rule. So I have these chains. Because I have these chains, these directional arrows, right, these directional acyclical graphs, what I don't have to do is I don't have to have x1, x2, x3, x4, x5, all these x's, right? I don't have to calculate the joint probabilities for each of them. I only calculate joint probabilities for its immediate predecessor, because I have a direction added to my Bayesian network. Okay? I'm going to not talk about the deseparation criteria because it's going to just make things worse. But overall, this is what a causal diagram then looks like. Okay? The beauty of this causal diagram, this is one slide that I'm going to talk about, then I'm going to talk a little bit about the, Simple example, this is directly from Pearl's Book of Why, very interesting. Simple example, but see what it can do. Prisoner X might be shot at the firing squad, right? So the court has to send an order to the captain. Captain asks two of his shooters. They shoot, leading to death. Okay, as of now, all binary outcomes to make things easier. The beauty of this, when you draw out a causal diagram like this, right? Here's a court order. The court gives an order to the captain. The captain says, whenever there's a firing squad, you have two people or more than one person shooting. Right? Because then the shooter doesn't know that he is the one who killed the person. Right? Takes away the guilt. Very wonderful ideas. So the captain talks to his two best shooters. They go and shoot, and the prisoner dies. Yes? Okay. Now, the beauty is any rung here can be removed, and still you would be able to answer the question of what happened. Unlike a machine learning algorithm or even a Bayesian network, a causal diagram allows you to take away any part of it. Think about it. Take away anything from here. If you take away one part of this and the rest of it happens, you still know what is the outcome. Court order didn't come. I blanked this out. But captain still gave the order. This part remains constant. What happened? The guy died. Court didn't. So this shooters didn't shoot. Both the shooters just decided, I'm not going to shoot. I'm suddenly become ahimsak. I don't want to shoot. Court order came, captain gave the orders, they didn't shoot, the person didn't die. Any part of this causal diagram can be taken out. Any counterfactual can be gauged, and you will get to know what is the outcome of the experiment or of the process. No machine learning or statistical model can really do that. Yes? That's why I believe, I don't believe, I know this is a revolution. It's going to change things. Because it's going to make things more human. Yes? Because human beings can do this. Okay? So now, to do this, right, we have to go and build the new theory. You cannot just start doing this stuff, right, and drawing pictures. You have to build a new theory. You have to build a new probability theory for this. And that is why Judea Pearl won the Nobel, the Turing Award, equivalent to the Nobel in computer sciences. The Arrow of Directionality. So what he did was that the first method, this is simple, probability of L given D, probability of increasing lifespan given he/she took the medicine. There is no directionality, only shows probability of L if we see D. We see D, what happens, right? What if the existence of D depends on multiple other factors which affect your chance of survival? Maybe you're healthier than the other person. Yes? All Pearl did, and that's the whole do calculus is based on that, is add a term called do, which says that probability of living given D. If you do D, not the visibility of D, but actually the instance of D being done, right? A medicine being given, a life-threatening disease being there. Also allows us counterfactuals. If you have do, you also have a do not. Right? This is in many ways somewhat similar, and this is another way of solving these problems, of a structural equation model. This is again back from Sanyal, right? Which is why it's very difficult to convince economists about these things. When you talk to economists, they say, oh, we learned structural equation models in graduate school. What are you saying that's new? Because structural equation models deal with something called instrument variables. Anybody who studied economics would know, looking at proxies and so on. Direction, still not there. Yes. Now, applications. I'm going to go straight to applications. I know we don't have too much time, and I want to go through a lot. The holy grail of causality is the randomized controlled trials, right? RCTs. Now, you say that, okay, RCT is fantastic. Banerjee, Duflo, Kramer, and co-authors, they won the Nobel Prize recently and so on. So the thing to remember here is it's not about just the algorithms, but it's also about the data collection process. RCTs, absolutely, but a lot of these experiments that we want to run or we want to think about are actually not randomized controlled trials. They are experiments that happen naturally. They're naturally occurring experiments. A policy intervention is done. You didn't choose when to do it. It just happened. Government came and did but did that intervention have an effect? That is where the work of Guido Imbens comes in, right? Who from the 1990s has been talking about naturally occurring experiments in economics. Imbens came up with something that's very interesting. The standard for experiments of any kind is the average treatment effect. We look at the people who are given the placebo, right, or not a part of the policy group. We look at the people who are given the medicine. We see what's the average difference between the two. The challenge with that, especially in naturally occurring experiments like an A/B testing, right, or a policy decision, is that people often don't comply with what they're told to do. Some people you gave the placebo, but not all of them had the placebo. Some people you gave the trial medication. After 7 days, they stop having it. So there are non-compliers, right? Your average treatment effect ignores that. So Imbens and others came up with multiple other things, among other things, something called a local average treatment effect, or LATE. What that does is it takes care of this non-complier problem. So two different ways of looking at something very, very similar. One is from an econometric standpoint. I'm not going to go into the details of it. But at the end of the day, all of you are going to say this, where the bleep is the library. You talked a lot. I want to do dot fit and dot predict, right? I don't want to care about all sorts of stuff that you were talking about. There is a library. So I was thinking about writing a library, but then the good people at Microsoft did it for me. So then I didn't have to spend the time. And Microsoft is big into causality. These guys are the ones who are absolutely, absolutely serious about causality. They're doing a lot. But it's new, right? The do-why library, Python library from Microsoft came out, what, a year and a half back? Yeah, 2 years back. Very, very recent, yes? This presentation will be, we will upload the presentation, so you'll have access to it. The beauty of the library is that it's a 4-step process, yes, for causal inferencing, which will explicitly model causal assumptions and validate them. If you remember Henley-Cox's last piece, which says that I'm going to draw blood out of that guinea pig, and that should have the biological agent that I'm expecting to cause the disease. So you have to figure out that if I try to refute my estimates, can I not refute them? So the test of causality is usually much, much stronger than something which we love, but it's absolutely nonsensical, the p-value, right? P-value is stupid. We know that. We still use p-values. Or I use p-values. I do it for a living, right? But this is much stronger than a p-value, because what you're trying to do is you're trying to refute the claim of this causal effect, right? So you're going back to that animal which you gave the disease, the biological agent. You didn't give the disease, you gave the biological agent. You extract blood from that animal and see that whether that biological agent is present if the animal has that disease, the new animal. So can automatically test causal assumptions for any estimation method, right? Supports a whole bunch of them, okay? There's a case study. This is just, you know, I'd let you guys take a look at it. I'll have the slides. I have about 6 minutes or so. Simple example of a membership being offered, right? This is standard stuff. And did that membership actually lead to people spending more time on the website or signing up for some program? This is the typical question that, you know, you get it's like that guy, right, who said that I got a PhD from Cornell and I'm trying to figure out if somebody's going to click on an ad. Yes? So this is the kind of stuff that many of us are trying to answer after you know, getting some advanced degrees. So you model a causal problem, you formulate it. There's a graph. Again, not a DAG, not a Bayesian network, but a causal graph. Yes. You identify a target estimate under the model. Yeah, I am nearly there. Identify the causal effect. Estimate the base effect based on the identified estimate, which we have already specified. And then finally, we try to refute the obtained estimate. Yes. Now, I'm going to go right away to talk about, you know, we talked about the economics of it, the econometrics of it, the computer science of it, and why, you know, this is so important. But what if there is no experiment in the kind of stuff that I do? Can I still do something? Yes, you can. Right? And this is, again, this is changing the way AI is going to be done. There's a book by Gerd Gigerenzer and his colleagues called Artificial Intelligence in the Wild. Very recent, 2001. Gerd, I know, I was in Max Planck for his summer institute, met him a few times, fantastic researcher, a legend in decision making. He is trying to emulate some of the things that Herbert Simon did. Herbert Simon is a legend, right? He's the founder of AI and he's the founder of behavioral economics, right? Of course, all of you know him, I'm sure. What Simon wanted to do was he wanted to take psychological models of decision making and behavior, right, and build an AI around that. Yes, so the first AI model was created by getting a room full of people and giving them a problem, asking them that how did you solve the problem, and then making the program emulate that. Right? This is before McCulloch-Pitts. Yeah? Because McCulloch-Pitts said that, oh, you know what? Psychology doesn't work for us. We are going to try to emulate the physiological process of human behavior or human thinking through a neural network. Herb Simon, I think, was a smarter man. He said that, look, it's like trying to figure out the physics of the weather or trying to figure out if I throw a ball at you, will you be able to catch it or not? You will be, right? But you're not doing vector mechanics for that. The wind speed, of course, and my weight, how hard I throw it, etc. You're not calculating all of that stuff, right? If you use physics to calculate the trajectory of the ball, that's what you have to use. But we all know that that's stupid. Yes? So what Simon did, I think, is way more intelligent than what McCulloch-Pitts landed up doing. What they landed up doing was to try to emulate the physiology of a neural network. Simon said that, it's not a game, right? Said that, the human psychology, the human brain, is much more complex and very good at estimating things very fast using something called a mental shortcut or heuristic. What we should do if we are trying to build an artificial intelligence system is to try to emulate the heuristic, not the brain chemistry, not how the messages get transmitted through the neural network. Yes, that way of thinking went out of vogue because a man called Daniel Kahneman came up with a lot of stories about how heuristics are stupid. Yes? Simon said heuristics are intelligent, makes us intelligent. That's why we survived, because we have mental shortcuts. Kahneman says, no, heuristics lead to stereotyping and stupid things like that. It leads to biases. Kahneman's correct. Kahneman and Tversky, of course. And for saying this and starting behavioral economics anew, Daniel Kahneman won the Nobel Prize. He's a psychologist who won the Nobel Prize in economics. But what happened in the process was Herb Simon's way of thinking about artificial intelligence and behavioral economics just went for a toss. But things are changing. At the Max Planck Institute, Gerd Gigerenzer and his group have been doing some fantastic work on simple heuristics that make us smart. Very, very simple heuristic algorithms, yes, which makes human intelligence. Human intelligence does not depend on the neural transmission of transmissions at all. Human intelligence at the end of the day depends upon our psychology. It depends, and our stupidity also depends upon that. Amos Tversky, Kahneman and Tversky, said that I don't study artificial intelligence, I study human stupidity. Right? Very famous quote. He was right. But our stupidity and intelligence come from very simple algorithms that we use in our mind, which are heuristics, yes. What's a heuristic? If I throw a ball, you will be able to catch it. I wrote about this a lot. You take a 1-year-old and show it a cat twice or thrice, the little kid knows what a cat is. Never makes a mistake rest of his or her life. They see a cat, they say cat, cat, cat. They know it's a cat. You teach your best deep learning model, what is a cat? Or what's a chihuahua, for that matter? You'll need 100,000 pictures, and then it's going to mess up every time it sees a blueberry muffin. Yes, you should go online and Google chihuahua and blueberry muffin. They look very similar. Unbelievable. Yes. So your stupid algorithm is going to make that mistake, but a 1-year-old child will not make that mistake because the child does not use neural networks. The child uses very simple heuristics to identify a cat or the catness of a cat. Yes. And that brings me to simple heuristics that make us smart. More new names. Yes, sorry. Lot of new names. But where is the freaking library again? You need a library, right? .fit, .predict. You don't care about what I said. You want, you at the end of the day, you're like, can I get a .fit, .predict and move on from here? We want to listen to the next speaker. 1 more minute. There is a library. Again, stuff that I want to do, other people do it before me, which is great. Saves me time. A guy called Nathan Phillips, so somebody called Laura Matillon came up with an algorithm called fast and frugal tree. A fast and frugal tree is much, much more frugal than a decision tree. A decision tree is quite stupid. It's a very greedy algorithm, as you know. A frugal tree is frugal. It works much faster than a decision tree, much, much faster. Because what it does is anytime something says no, it chops it off. It auto prunes a tree, makes it yes, no, yes, no, yes, no, moves very fast. That's exactly how human beings take decisions. We don't use decision trees, we use frugal trees. Yes? There's a library in R, it's called ffTrees. There's a library in Python called FastTrees. Nathaniel Phillips built the first one, and then based on that same algorithm, recently. So you see, the moment I'm not interested in something, I just truncate that part of the tree and move on. Condition 1, action 1, it's done. I move on. I don't even wait to see what happens afterwards. I only look at the false part. Condition 2, action 1. If it's false, then condition 3. What sort of actions? The very famous example is that whether a doctor decides upon a particular emergency procedure when somebody has come into an emergency room. They do not have time for a decision tree at that point. They would take a decision based on, okay, is BP higher than this? Yes, no. Is the age higher than this? Yes, no. Right? 2 or 3 at the most, done. That's the kind of stuff that a fast and frugal tree tries to replicate. Yes. Because human beings are smarter than computers, and we take decisions like this. Yes. All right, so there's an example of a smart and frugal, a smart heuristic, fast and frugal trees. I won't talk about it, but I'm going to end with one last thought for all those who thankfully listened to me for so long. Before I end, I know that we're running late, that there are a bunch of physicists who have gotten interested in the social sciences. Yes, I've been to a bunch of their conferences, and sometimes I realize that they are physicists. They don't understand social sciences or economics, but there are some who are fantastic. They use certain things which, again, as machine learning practitioners, we completely ignore, like agent-based modeling. Think about it. There are so many ways to bell that cat, but nobody in this room probably has worked on causal inferencing based on Pearl's work before, right? There is somebody. Okay, good, one person. Anybody who has used a fast and frugal tree before? No? Anybody who's used Guido Imbenz's local average treatment effects before? The guy won the Nobel Prize a year back. He was all over the news. His wife is going to win the Nobel Prize as well, Susan Athey. She's a fantastic economist. And agent-based models. How many of us have done agent-based models? All I'm trying to say is that causality is what we want to get at. Yes? There are many ways of doing it, like there are many ways of doing data science. Just because one way has gotten extremely popular, right? Let us not just herd towards that. Abhijit Banerjee's famous paper on herd behavior. We all herd and we say, oh, this is easy because I have dot fit and dot predict. This is stuff that they teach me in every course in data science available in the market. I can get a master's degree in data science without knowing any of this stuff. Right? Because science also has, flavors of the season. What is fashionable? Machine learning is fashionable. AI, in this way of doing AI is but there are many other ways of doing artificial intelligence. There are many other ways of understanding that whether A actually causes B or not. And this talk was just an attempt to get all of you excited about it and to probably just read more, try out the libraries, figure out what NetLogo is. I teach at adjunct faculty at Northwestern University as well. They have a program called NetLogo. And it's been around for a long time, which allows you to do these agent-based models, beautiful agent-based models. There's also something called gamma. You have different kinds of agents in a geographical location. You put them together. You have different kinds of traders in a financial market. You put them together. You give the assumptions and see what happens. Right? We don't see it like that. We aggregate everything under the current paradigm of machine learning, and that, to me, is extremely unfortunate. We're losing out a lot of good things. Yeah. So that's all I had. Thank you so much for listening to me. And if there are questions, I'll be around. The next speaker needs to get on. So I'll be right outside, so if you want to talk to me, I'm happy to answer any questions.